It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi, welcome to the second part of 4.2 water for the managing resources topic. In the first part of the video we had a look at water, the processes of purifying it. We talked about coagulation, flocculation, we looked at cleaning agents, and we also looked at how they use reverse osmosis to purify water, and we looked at the desal plant here in Adelaide. So if you haven't watched that video, I suggest you go back and do that first. In this one we're going to continue on looking at just some processes for purifying water and then also disinfecting it as well if we need to. So apart from also using reverse osmosis to purify water, one of the new ways they're using it is through thermal distillation. So thermal distillation is where we boil salt water at really high temperatures. What that does is that causes the water molecules to evaporate, leaving the salt behind, and then cooler sections up the top cause it to condense back to a liquid, and we collect that. So you can see over here in our heating chamber, we're heating up our salty water. Okay, the water particles come up the top, they come up to this cool water up top, they condense on the surface here, run down, and we can collect it over on the side. The downside of this is that you obviously need massive amounts of energy and fuels to create the heat you need in order to vaporize the water. You are still left with a salty residue at the end as well, which is a downside. But this is quite common in third world countries in particular, or countries where there is a large supply of fossil fuels, where they don't have to worry as much about fossil fuel supply. They are quite happy to burn it in order to produce pure water. It's obviously a lot easier than trying to do reverse osmosis or some kind of desalination plant, particularly if you're not near the coast. If you're in the middle of the country and there's no salt water readily available around, this is another way of getting pure water from perhaps groundwater reserves or other places like that that need to be purified. Once you've got your water, the very final thing they'll want to do is normally disinfection, and this is to remove any bacteria or microbes which might be in the water. Now those microbes won't be removed through filtration or sedimentation or anything like that, and what we normally do is use either chlorine or chlorine containing compounds. So chlorine is just ClCl, so Cl2. Okay, and it helps, not only does it kill off bacteria that's in the water, but it also prevents bacteria from growing and makes it safe for us to use. So sometimes when you turn on the tap you might smell a bit of chlorine smell, depends on how much they've had to treat it that day, as to whether you'll actually be able to smell it or not. And chlorine is quite a poisonous gas. It was used during World War I as one of the toxic gases, but obviously we're using it in much more controlled ways when we're looking at water purification. Okay, so if we take chlorine gas and we dissolve it in water, we form hypochlorous acid, and this is a mistake here, sorry, this should be Cl2 in a gaseous form, so I'll just correct that for you, sorry, so that should be not drawing, that's all right. It should be Cl2 gas plus H2O forms HOCl. Now HOCl is what we call hypochlorous acid, and it's made up of two parts. It's made up of a hydrogen ion, which all acids are, and it's made up of this hypochlorite ion here, OCl-, that's the hypochlorite ion. We also get hydrochloric acid here. So obviously dissolving chlorine in water gives us quite an acidic solution, which is what you'd expect because non-metal oxides are acidic. Now there's an equilibrium within this water treatment, alright, and one of the things you'd be expected to do is be able to talk about the effect on the equilibrium when you change the pH. So I suggest if you haven't got a good grasp of equilibrium, you go back and watch some of those videos to understand the whole process and principle of the Chatelier's principle, where an equilibrium shifts to counteract a change imposed upon it. So if we decrease the pH, what we're doing is we are adding H+. Okay, so if we're adding H+, what we're doing is we're increasing this concentration. Okay, now what the equilibrium is going to do is it's going to shift to try and decrease that. So what happens is the equilibrium shifts to the left to decrease this H+ concentration. So it's going to decrease our hypochlorous acid concentration and increase our chlorine gas concentration. Now, if we decrease our hypochlorous acid concentration, that means that this is the thing that actually gets rid of the bacteria. So we're reducing the ability to oxidize the bacteria and kill it. Alright, hypochlorous acid, oxygen gas, they're all very, very strong oxidizing agent. They can penetrate the cell wall and oxidize within the cell, and that kills it. Alright, so if you decrease the pH, you're going to have an impact upon how well you can actually kill off the bacteria. Obviously, if you go the other side and you increase the pH, these acids, they're going to get neutralized by the basic solution you're putting in, and so that's going to decrease the amount of HOCl you have as well. So it's important to have a good balance in terms of your pH. Normally, you're looking around 7.2 to 7.8 is a good pH, depending upon the cleaning agent that you're using. So here's that equation again. If we increase the pH, as we said, the OH minus ions react with the H plus. What this can do is force the equilibrium to the right to increase the HOCl. Okay, but what will happen is if you keep increasing the pH, you'll use up your HOCl by neutralizing it as well, and so you don't want to go too basic with it either. So that's why we go 7.2 to 7.8 to push it slightly to this side to increase HOCl and make sure we've got plenty of that there to keep the bacteria killing power of the cleaning agent readily available. Hypochlorites are also used as common disinfectants in commercial bleachers or swimming pools. So here's an example of something you might add to your pool, which is calcium hypochlorite. Okay, and so it doesn't really matter what your cation is here. We want to have hypochlorite ions. Similar to the previous one, we dissolve chlorine gas. When you dissolve hypochlorites in here, you get again your hypochlorous acid. This time, instead of HCl, we have OH minus. So if we have a high pH, it's going to increase the concentration of our OH minus. Equilibrium will shift to the left to decrease the concentration of OH minus, so that reduces our amount of HOCl. If we have a low pH, the H plus reacts with the OH minus, and so this goes to the right. Okay, and what happens is your HOCl gets increased. Now you'll see this in swimming pools quite regularly. If you've been in a swimming pool and you get red stinging eyes, that's normally an indication that there's too much hypochlorous acid in there, and that's the reason you get your red eyes. If there's not enough hypochlorous acid, hopefully you haven't been in one of these pools, you'll notice there's a lot of algae present and it's green. So yeah, pool green, no swim. That's my advice. So obviously you want to keep your pH quite specific to make sure that your hypochlorous acid concentration is at the right level to be able to kill your bacteria. And as we've talked about, here's a bacteria, rest in peace, little ugly bacteria. A slightly alkaline solution is preferred because it just allows our hypochlorous acid concentration to be high enough that it will kill the bacteria and it won't cause that red eye or damage to humans. Okay, and this is one thing you might want to remember. Alright, so they kill bacteria by penetrating the cell wall and oxidizing the cell contents, preventing cell reproduction. Hypochlorous acid is a stronger oxidizing agent than the hypochlorite ion or chlorine gas, so hypochlorous acid is really what we want to use. Alright, that's the end of this part for water. I suggest you go back and really make sure you know the steps that we go through with water purification. So we go through normally flocculation and getting rid of the sediment in there. We go through a filtration and purification stage, and then we go through a disinfection. Again, it doesn't necessarily mean we're going to use all of those. It depends on where the water comes from as to what processes we use to make it potable, so drinkable for humans. But I suggest you can go through and know those processes, and then you obviously need to be able to explain how surfactants or cleaning agents work, and then you need to be able to explain the equilibrium that is existing within cleaning agents for killing off bacteria, which is what we've just been through. So as always, if you've got any questions, just ask, and I'll just leave you again about the importance of pure water with this little clip. Thanks, guys.
Bobby! Water sucks. Gatorade is better. What? Use it on the field. Gatorade not only quenches your thirst better, it tastes better too, idiot.
You're drinking the wrong water.
Gatorade.
H2O.
Gatorade.
H2O.
Water sucks. It really, really sucks. Water sucks.
No, stop
it
saying
really,
that.
really
You don't mean that.
sucks.
You're bad people.
Oh!